Welcome to a lesson on rewriting triple integrals using cylindrical coordinates. This video does assume that you're familiar with the formulas used to convert between cylindrical and rectangular coordinates as we see here and here. So you may want to write these down for reference. Let's go and take a look at our first example. We want to rewrite this triple integral given in rectangular coordinates using cylindrical coordinates. So the order of integration here tells us a lot. Notice we're integrating first with respect to z, which tells us z is on the closed interval from 0 to 2. Y is on the closed interval from negative square root 1 minus x squared to positive square root 1 minus x squared. And x is on the closed interval from negative 1 to positive 1. And when converting from rectangular to cylindrical coordinates, the xy trace is often very helpful. So if we take a look at this compound inequality here, and look at the equation y equals the square root of 1 minus x squared, if we square both sides of this equation, and then move the x squared term to the left side, we'd have x squared plus y squared equals 1. So the xy trace is a unit circle, and then based upon the given inequality, we know the region in the xy plane is inside this circle. So let's see if we can take all this information and rewrite this using cylindrical coordinates. Now let's take a look at our integrand. We have the square root of x squared plus y squared. X squared plus y squared is equal to r squared, and the square root of r squared would be r. And then remember, when converting to cylindrical coordinates, we have an extra factor of r, and then dz, dr, d theta. The limits of integration for z, they were given to us in the original integrand. It's going to be from 0 to 2. And then for the limits of integration for r, we can take a look at our xy trace. R will start at 0 and then go out to 1. So limits of integration are from 0 to 1 for r. And then for theta, we want this entire circle, so we'll start at 0 radians and go all the way around to 2 pi. So in cylindrical coordinates, this integrand is going to be much easier to evaluate. Let's go ahead and rewrite this as r squared. And before we integrate, let's go ahead and take a look at the solid region of integration defined here in rectangular coordinates and here in cylindrical coordinates. And we can see that we have a cylinder bounded by z equals 0 and z equals 2. This is our region of integration. Integrating with respect to z, treating r squared as a constant, it'll give us r squared z Now when z is equal to 2, we'll have 2r squared, and then when z is 0, we'll have 0. So we'll have 2r squared dr d theta. And now we'll integrate with respect to r. We have 2/3 r cubed. Well, when r is equal to 1, we'll have 2/3, and then when r is equal to 0, we'll have 0. So we'll have 2/3 theta, evaluated at 2 pi and 0. Put this over 1. So the result here is going to be 4 pi thirds. Let's go and take a look at another example. Again, let's start by taking a look at the order of integration and then the limits of integration as well. This tells us that z is on the closed interval from x squared plus y squared to 4. Y is on the closed interval from negative square root 4 minus x squared to positive square root 4 minus x squared. and x is on the closed interval from -2 to +2. And let's go ahead and take a look at the xy trace again. If we treat the right side of this as an equation and we square both sides, we'd end up with x squared plus y squared equals 4. And this tells us that our xy trace would be a circle with radius 2, as we see here. And this region inside the circle is going to help us determine the limits of integration with respect to r and theta. Let's take a look at this solid region of integration before we start. So here we have the paraboloid z equals x squared plus y squared and the plane z equals 4. So our region of integration is the solid below the yellow plane inside this paraboloid. So notice that what we call the xy trace is really the z equals 4 trace, but it is the trace that's going to help us determine the limits of integration for r and theta. Let's go ahead and set it up. Y is equal to r sine theta, and then when converting to cylindrical coordinates, dz, dy, dx gives us an extra factor of r, and then dz, dr, d theta. Now let's take a look at the limits of integration for z. We know z is bounded by x squared plus y squared and 4. Well, x squared plus y squared is equal to r squared, so our lower limit of integration will be r squared, and the upper limit of integration will be 4 for z. And then for r and theta, we'll take a look at this circle here. The radius r will start at 0 and go out to 2. And then for theta, we want to start at 0 radians and go all the way around to 2 pi. Let's go ahead and rewrite this. We'll have r squared sine theta dz, dr, d theta. Let's go ahead and evaluate this on the next page. Integrating with respect to z, we're going to have r squared z sine theta Now we'll replace z with 4 and then z with r squared. So we'll have 4r squared sine theta minus r to the 4th sine theta. And now we'll integrate with respect to r. So we'll have 4/3 r cubed sine theta minus 1/5 r to the 5th sine theta. Evaluate here at 2 and 0. Let's go to the next page. So when r is equal to 2, we'll have 2 cubed times 4/3. It's 32/3 sine theta minus 2 to the 5th is 32, so we'll have 32/5 sine theta. And now that we have like terms, we can go ahead and combine these. This gives us 64/15 sine theta and now integrating with respect to sine theta, we're going to have negative 64/15 cosine theta. Now the result here is going to be a little bit unexpected. We're going to have negative 64/15 and then cosine 2 pi would be equal to 1, and then cosine 0 is also equal to 1. So the result is negative 64/15 times 0, which is equal to 0. And that's going to do it for this video. Thank you for watching.